This is related rates example number 2. So in this problem, we have a television camera at ground level, and so that's not what I needed. Get that. That's right there. There's the camera, and it's filming a space shuttle that is traveling at some speed, and its position is given by 50t squared. And so we want to know if the distance between the camera and where the space shuttle took off was 2,000 feet. We want to know, how does this angle theta change with respect to time, right? So as the rocket shoots up, the angle is changing, and so we want to find that rate. And so if we want to list out what we're looking for, we're going to find d theta dt, right? We're looking for the angle when t equals 10 seconds. Okay, and so from that, we can find some more information. If t equals 10 seconds, that means our space shuttle traveled for 10 seconds. So at 10 seconds, my s is equal to 50 times 100, and so 5,000 feet. Okay, and so again, we have to relate what we're looking for. We're looking for our rate of change of this angle to the other variable that's changing with time, which is s. The 2,000 is constant. And so if you look here, we can relate it using tan. So tan theta is equal to 1 over 2,000 times s, right? Tangent is my opposite, s over my adjacent, 2,000. And so to get d theta dt, we have to take the derivative of both sides with respect to time. And so the derivative of tangent gives us secant squared theta. And then the derivative of theta is d theta dt. I'm going to take the derivative with respect to time on the right-hand side. And so that's 1 over 2,000. It's a constant, so I just leave it there. Times s, or the derivative of s. And so that's going to be ds dt. And so we're solving for d theta dt, and so that will give me 1 over 2,000. Now when we divide by secant squared, right, 1 over secant squared theta is actually cosine squared theta. And so I'm going to replace that and say cosine squared theta times ds dt. So the question now is, what is ds dt? Well, ds dt is how the position changes with respect to time, and well, that's given from taking the derivative of the position function. So that's 50t squared. And so ds dt is equal to 100t. And so d theta dt equals 1 over 2,000 cosine squared theta 100t. And so now we need to figure out, well, what is cosine squared theta? Well, cosine is my adjacent over my hypotenuse, and well, if this is 2,000 and at t equals 10 seconds this is 5,000, my hypotenuse would be given by 5,000 squared plus 2,000 squared. And so to find d theta dt, I can plug these values in now. D theta dt is 1 over 2,000. Cosine squared, well, cosine theta is going to be 2,000 over the square root of 5,000 squared plus 2,000 squared times 100 times t. And t is 10. So let's change that to a 10. And so now we have all our values in there. And so now we can find that our theta is changing at a rate of 0.069. And now we need to the units. And since we're talking about an angle here, we're going to say radians per second. And so here we found how the rate of change of the angle of elevation of the camera is changing at t equals 10 seconds after liftoff.